It's a great pleasure to introduce Mike Wilson from University of Vermont, and he will speak about perturbed Haar function expansions.
Thank you. And thanks to the organizers for this invitation. And again, as I already said, thank you for letting me delay this by 2 weeks because we had family visiting, and this way we got an extra day, or at least I got an extra day to spend with our son's family visiting up from New York. Okay, so here goes. I'm going to, I'm sharing this screen. I'm going to, here's my web page that has all the whole talk up there. I guess I'll send the link out later. Here's the talk. There we go. And let me a little bigger. Perturbed Haar function expansions. Just to repeat the abstract, make it a little bigger. So we're all familiar with the Haar functions, which I'll define a little bit later, but we're all familiar with them. They're an orthonormal system for L2, and they're unconditional basis for LP. Namely, this.
Sorry, can you zoom more? Can you like zoom in, not zoom? Like it's a bit small.
Make it small?
No, make it bigger. Yeah.
Okay, I'm trying to make it bigger. Is it big? Is it big enough now?
More, yeah, even more. Could be a bit more.
Okay, how about that? Control plus. Is it big enough?
That's good. Yeah, that's good. Yeah.
Okay, sorry. Yes, if anything like that happens, please tell me, and yeah, I'll. Your wish is my command. Okay, so if for any F and LP, we can write it as in this form. Okay, in LP, this sum converges unconditionally. Okay, and this means the usual inner product. You can also readily generalize the Haar functions in D dimensions, and I'll show explicitly how that's done a little bit later. Not hard, and you have a corresponding sum. Now, what I'm going to be looking at is the stability of this kind of expansion when the Haar functions are mucked up. If you perturb them, okay. You suppose you have a bunch of numbers, alpha I, twiddle, and alpha I star, and also also other numbers yi and y twiddle star. The alpha i's are all close to 1. The yi's are all small. So that's what this means here. We just say that the 1 minus alpha I absolute value plus yi twiddle, standing with the stars, are small. And then you use these to build perturbations of the Haar functions. Basically, you see alpha I twiddle, you basically shift it from the center, and you add a little thing that's scaled according to the length of the interval, and then you add back the center. So it's like a little shift plus dilation centered around the center of the interval, and a corresponding thing for this, okay, for the other Haar functions. Then these sort of perturbed Haar functions, are in a natural sense, it looks like they're probably close to the original Haar functions, and so you expect that this kind of expansion should be, close to F, and in fact we'll show that if you have this factor eta here, which is scaling the size of these perturbations. In fact, this distance in L2 is no bigger than a constant times eta to the 1/2. Okay. In fact, it's easy example to show the eta to the 1/2 is sharp. And also in LP you have something similar. Notice you can have a perturbed guy here. You have to have the original one here, and you'll have this inequality here, the stability result, so to speak. As long as P is bigger than 2. I can't do it for P less than 2. And what's difficult about this, what I should point out, is that the Haar functions have discontinuities that you can't ignore. Okay, they have non-removable, jump discontinuities. And what this turns on is proving things like this is basically a way of getting almost orthogonality of families of functions without asking that the functions be smooth in any natural sense. Okay, so that's the abstract and so on. Now this is coming here, the sort of a repeat of what I just said. If you have a complete orthonormal set for L2, then of course you have this series converging unconditionally in L2 to F. And then it makes sense that if you have two other families of functions that are indexed on this big set gamma here, this one and this one, and if they're in some natural sense close to the original functions, then this should be small, okay? and you would like that this should be smaller than a constant times f times L2 norm, and the constant should go to 0 as these and these get closer and closer to the originals, okay? Okay, so as a model case of a problem like this, okay, the stability of almost orthogonal or even complete orthonormal expansions, we'll look at, the Haar functions, okay? So here are the Haar functions explicitly defined. You have the dyadic intervals, which I think everyone is familiar with. And for every dyadic interval, you have I have sup I of x is equal to the measure of I to the -1/2 if x is in the left half of I, the interval, and it's negative measure of I to the -1/2 if x is in the right half of the interval. Then if you take this family where you have the h super I and then normalize them, dividing by the measure of I, I'm sorry, that's a mistake. That should be a 1 and a -1. I apologize. 1 and -1. Oops, I apologize. Typo. That should be a 1. That should be a -1. Here I want this. So then this would be the Haar functions. I apologize for that. Okay, 1, -1. I'll fix that when I put these up there. Okay, so these are orthonormal, and a little more work shows them to be complete. Okay, so so they're easily generalized to RD or the cube. Cube will be expressed as a Cartesian product of D intervals, all having the same length. Q is denoted Cartesian product of the intervals like this. The geometric center of Q is x sub Q, standard thing. And then for every Q for every dyadic cube, we can define 2 to the d-1 functions like this, HQD like this. HQK of x is just this product, functions GI of xi, where GI can be either the Haar function, that is, it's plus or minus 1 Haar functions that I should have had, or the characteristic function of the interval, but you don't allow the product where they're all where it's chi q. Okay, then this is readily seen to be a complete orthonormal system for L2. Okay. So, and then the corresponding result for unconditional convergence of the Haar function expansion applies. Okay, with of course written correctly. Yeah. Okay. Now the first result in the abstract is the one-dimensional form of a theorem that I'm going to state and not prove in all generality because it would take forever. So we can phrase it using this L infinity norm for a matrix. If B is an m by n matrix, then the L infinity norm of this matrix is you take the sum, you take the row sum for the ith row, absolute value, you take the max as the familiar object from matrix theory. This is the operator norm of this mapping going from Rn to Rm, where x is being treated as an n by 1 vector. Okay, so the theorem stated in the abstract is a one-dimensional version of the following. Okay, suppose if you have this convention here for the L infinity norm of a matrix or a vector, there are positive constants C of D and C of D, so let the following hold. Suppose that for every Q, dyadic cube, and every K in this range, you've got 2 real D by D matrices, this, and 2 vectors here, so that, again, the distance from this matrix to the identity plus the size of this vector, distance to the identity, size of this vector less than eta, where eta is small and fixed. You can then use these vectors plus matrices to again define basically Q-centered, perturbations, distortions of these Haar functions, where you might, maybe twisting them and expanding them a bit and shifting them a little bit like that. Okay, then this, if correspondingly for these Haar functions here, then for every f in L2, this perturbed Haar function expansion converges unconditionally, and it's not too far from f. Okay, constant in D, eta to the 1/2 FL2. Okay, now I explored this question. I was interested in this because I was trying to understand how perturbations like this might affect discretized wavelet families, and I'll say a few words about how the discretization itself affects that later. And the Haar functions seem like a natural model case. Okay, this theorem, it's proved, it's in a paper that I'm sending around now. it's proved by getting, the way you prove it is you get what are good bounds on a sort of an almost orthogonal distance between the family of Haar functions and their perturbations, okay? And for which, as I said earlier, the chief difficulty comes from the fact that the Haar functions are discontinuous, or the discontinuities, okay? So I want to explain what this all amounts to here, okay? So a set, size of gamma, gamma and big gamma in L2 is called almost orthogonal if there's a constant like this, so that for all finite subsets of big gamma and all finite collections of complex numbers like this, then the L2 norm of this is bounded by b times the sum of the squares square root, okay? And if b is the smallest number for which this thing holds always, then b is called, it's almost, this family's almost orthogonality constant, or almost orthogonality norm, okay? Now, by an easy duality argument, this is almost orthogonal with constant b if and only if for all f in L2, you have this inequality holding, and b is the best constant, okay, for which it holds. It's a little easy, very easy, almost orthogonality, almost a very easy argument, okay, using duality. Now, for any non-empty set gamma, of course, you can turn this collection of almost orthogonal families, index over gamma, into a vector space in the obvious way. You add families together like this, you multiply them by scalars like this, the usual, okay? And you give it a norm like this, the almost orthogonal norm, so to speak. It's a soup of all these L2 norms where you're looking over these finite sets that sum of the squares is less than or equal to 1, which of course gives you the almost orthogonality constant, okay? Now the relevance of almost orthogonality to our perturbation question comes like this. Suppose you got some complete, say a complete orthonormal set, okay? And you've got these other things here, this set of functions, this set of functions here, and there are two families which are close to the original family here in the almost orthogonal sense. So suppose that this difference here and this difference, they're almost orthogonal norms bounded by delta. Well then, very simple manipulations show that then this sum, I'm basically using these two forms of being almost orthogonal, these two bounds, will converge unconditionally to something in L2, and it won't be too far from F, okay? Okay, delta 2 plus delta F, okay? So great, so the almost orthogonal norm gives you a way to like measure deviations from functions having like a good property, like being a complete orthonormal system. It also gives a way to quantify the effects of perturbations on frames. So if this is called a frame, if there are constants A and B, usual definition, so that for all F and L2, you have this, these two bounds holding. And then of course, if A and B are optimal, we call them the frame constants or frame bounds. And now it's pretty clear that if we have another family, which is close enough to psi gamma in this almost orthogonal sense, then of course this will also be a frame with nearly the same frame constants. Okay, so this seems like a natural question. And if you look how almost orthogonality is used in the literature, like proving like multiplier results, it's used to control junk. Okay, in a way, the proof of the T of 1 theorem is like, it's an almost orthogonality result lies behind it. You have operators with sort of perfect cancellation that are obviously L2 bounded, and then you muck them up by a perturbation term, which you control using that, the T of 1 in BMO is basically saying that the junk is small, and it turns out to be basically an almost orthogonality estimate. Okay, so now given this, theorem 1, that's the one that was back here about the stability of these almost orthogonal systems, will then hold if you could prove the following. And suppose you define our big set gamma to be this, and then if you have this and this, meaning what they did in the theorem 1, then this difference and this difference are both in almost orthogonality, almost orthogonal size, are very small, and then that would then imply theorem one. Basically, you want to show that if you perturb these things, their almost orthogonal size of the difference is small. Okay. Now, henceforth, I'm going to forget about this k up here, and just look at the q, the index being indexed over q. So I'm going to look at families of measurable functions from Rd to C, which are indexed over the dyadic cube, such that first of all, for every q, the set where fq of x is non-zero is contained in q. The L infinity norm is bounded by 1, and the integral is 0. Okay, so so cool. And we're going to look at ways to bound things like this. Okay, this difference where fq minus fq twiddle. Fq twiddle is a perturbation like those defined in theorem 1, where you basically have q-centered dilations and small translations. Okay, but of course, before doing that, you have to get some idea of, well, when is a family like this that satisfies A, B, and C almost orthogonal? Okay, and there are two ways to traditional ways to do that. Okay, you can first of all require that every fq be constant on each of q's dyadic children, immediate dyadic subcubes. So that would mean that fq is no bigger than 1. So here I got it right, the normalization right. Fq, the size is no bigger than 1. It might be plus or minus 1 or something on the dyadic subcubes, integral 0. And I'm going to call such a family Haar-like. Okay. And the other way is to ask that these fq's satisfy some scaled Helder condition. You ask that for some fixed alpha between 0 and 1, this difference here, fqx prime, be bounded by x minus x prime divided by L of q raised to the power alpha. Okay, for every q and d and all x and x prime and Rd. And this yields what are sometimes called adapted functions, although I think that's kind of an old-fashioned term. I'm going to call them wavelet-like. Okay. Now, both of these types of families, you see these conditions a lot in the literature. They give you almost orthogonality for basically the same reason, and namely that is that the inner product of fq prime is suitably small. Okay. In the Haar-like case, this difference here is 0 when q does not equal q prime, and I'm going to say this inner product rather is 0 when q does not equal q prime, because if q prime is contained in q, then of course this guy is constant on q prime, where this guy has interval 0. So there you go. And of course, where q equals q prime, this inner product is no bigger than the measure of q. Okay. So what you say, what's happening here is that these guys here, the fq's, are effectively smooth relative to each other. They don't see each other's discontinuities. Okay. Now for the adapted functions, you have something that's not quite as good. If q prime is contained in q, then if you take really, really lazy estimates, this inner product, fq prime, is bounded by d to the alpha, measure of q prime, and then you have the ratio of L of q prime over L of q to the alpha. And if you look at anyone who deals with these things, look at the CBMS thing that Razor, Yaworth, and Weiss did, many years ago, and everyone who works with these adaptive functions, this is good enough. This is good enough to give you almost orthogonality. Okay, in fact, this estimate here is not even optimal. So what you basically have is traditionally you augment A, B, and C, these three conditions, by what is basically a smoothness, a pointwise smoothness condition to get almost orthogonality. Okay, and now one problem with the functions we're working with, the Haar functions, is that if you perturb them, you no longer have either type. Okay, the smoothness condition is totally destroyed. Okay, wavelet-like families, by the way, I should mention, are really good with respect to these perturbations. Okay, and this is not hard to prove. If you have a wavelet-like family, and you perturb it in the way I've described with the matrix and the perturbation by a small translation, then in fact this difference here, its almost orthogonal norm, is actually bounded by, well, eta to a power. Okay, and the power depends, well, the power can be anything less than alpha. And the reason is actually quite simple. If you have, for example, if you have two functions, if you have a function that's in say lip 1, and you apply a translation like this to it, okay, move it a bit. How close is this function to the original function in lip 1/2? Turns out it's like taller than 1/2 away, okay? So, and then for other lip or Helder bounds, something similar works. So it's not hard to prove. But the perturbed Haar functions, you can't do that. There's no smooth condition. There's nothing you can really work on to do this. So to treat perturbed Haar functions and also to treat in general discretized wavelet functions, needed a new sufficient condition for almost orthogonality. Okay, and this is one that's based on bounded variation. Gali and Dimitri, they saw a talk about this about almost exactly 6 years ago. Just say a complex valued function f is a bounded variation. If there's a finite m, so that for all finite sequences in I and ordered like this, the usual, the sum of the absolute values is bounded by m, differences of the absolute values, absolute value of the differences bounded by m, and then you can define total variation and so on and so on, the supremum of this, and in the usual way. Okay. You can do this, of course, for intervals that are bounded, unbounded, open, closed, half open, and so on and so on. Okay. With that in mind now, okay, we can say that if f is defined in RD, we can say that f is of NBV. This is normalized bounded variation on RD. If it's measurable, and if for every y in RD and every standard coordinate vector, EK, that is unit coordinate vector, then this function, phi EK of y, of going from R to C, defined like this: phi EKY of t is f of y plus TEK, is a bounded variation on R, and its total variation is bounded by 1. Okay. If Q is a cube, we say that f is an NBV of Q. If it's an NBV of RD, and it's basically supported inside Q, and its integral is 0. Okay. So what we're saying is that basically f is of uniformly bounded variation along lines parallel to the coordinate axes, and the total variation is always less than or equal to 1. That's what NBV means. Okay. There's a companion notion, SNBV, strong normalized bounded variation, which I won't say a whole lot about, which basically just says the same thing as NBV, but it's that you now have to have this total variation condition apply to all lines in RD. Okay. And we'll be talking about families where every function in it is of NBV of Q for a family of cubes. We call those NBV families. Mainly I'll be talking about NBV, but SNBV will also come in. So now, obviously, SNBV is a subset of NBV in any sense. Note that if a family is Haar-like, then every FQ is equal to 4 times the function in NBV. Okay, and a little work shows that in fact it's not too big a multiple of an SNBV function. That's because there's a little like pigeonhole principle argument. If you draw a line through a dyadic cube, it can't hit too many of Q's children. Okay, it can only hit d plus 1 of Q's dyadic children. And if f is wavelet-like for alpha equals 1, then you have corresponding things about f being an NBV of Q, and it's not too bad times a function of SNBV of Q. Okay. Now, this is a theorem that Dimitri and Dalia saw the proof of about 6 years ago. Suppose you have an NBV family. Okay, so this is a family of functions, each one indirect over the dyadic cubes, each one satisfying uniform bounded variation condition with respect to lines parallel to the coordinate axes. Then that family, number 4 back there that I drew here, this guy here, FQ over Q to the 1/2, then that family will be almost orthogonal, okay? And it's all almost orthogonal size is not too bad. 1 plus 1 over radical 2D. And that's kind of unusual because these things here can have discontinuities that, for example, do see each other. and that are bunching up and building up in crazy ways, and yet the almost orthogonal size of this such a collection is not too bad. Okay. So so now thinking about theorem 2 of the perturbations of the Haar functions. Theorem 2 and thus theorem 1 follows this way. Suppose there are positive constants again, so that the following holds: if eta is small enough and yq and aq are again small vectors and matrices close to the identity measured by that infinity norm, and you have this an SNBV family, then you perturb each of these by this, then this family here is almost orthogonal size is not too big. Okay, so these perturbations don't screw up the almost orthogonal property too much. Okay, they don't move them away from each other in terms of being approximations. So what we're going to do, we're going to prove theorem 3. I'll show you theorem 3. That'll be, I apologize to Gali and Dimitri. They've solved this before, but I think the ideas will illuminate. The idea behind the proof of theorem 4, okay, which I will only give with dimension equals 1. Okay, so I'll prove this, and then I'll show this for d equals 1. And then I'll say a little bit about the consequences of theorem 4 for LP when P is larger than 2, right? Okay. And then say a little bit about what happens in higher dimensions. Is there a question?
Yeah, sorry, Mike, maybe I don't remember so well. So is this the theorem where you had these different blobs? I remember.
Yeah.
Blobs on the board. Yeah. Okay.
Yes, there was. Yes, there was there was a corollary of this, and that was if you had, suppose you have functions fq, and each one is equal to a linear combination of characteristic functions of convex subsets of q, and you just ask that the resulting functions here have integral 0, and also that the coefficients be bounded by 1, and that there are no more than n convex subsets. Okay, then so you could have I guess I need a whiteboard here to draw this. So how do I do that? Need a whiteboard.
Well, you could read, but then you'd lose your thing. So but you could also annotate directly on your picture there. Do you have something to draw with?
All I have is a mouse. Boy.
Okay, maybe too complicated to try.
Too complicated, but the thing is, you could have a multiple of an NBV family, for example, could be, say, a linear combination of n characteristic functions of convex bodies. Okay, where the coefficients in the linear combination are all bounded by 1, and you just have that the FQs have integral 0. Then in fact, and so then if you then build these FQs this way, and they could be convex bodies that are intersecting in crazy ways inside each dyadic cube, then you would have a family like my family 4, that equation I had back there, and that family would also be almost orthogonal, but its size and its almost orthogonal size would be no worse than 2n times this. Okay. So even though you have these families that have inside each dyadic cube, they have complex blobs that are intersecting in weird ways. You have this is saying that there's some sort of subtle cancellation going on here. Okay, which will say that the L2 size of linear combinations of these things divided by, of course, the measure of q to the 1/2. Not too bad, not too bad. And I thought that was kind of crazy. Okay, so I mean, they don't need to be like the convex bodies don't need to be like the dyadic subcubes. They can be ellipsoids, they can be tetrahedra, and so on, intersecting in crazy ways. But yet you get a function you get a family of functions that is, almost orthogonal with a not too unreasonable constant. So did I answer your question, Valia?
Yeah, that was one question. I had another question, but I don't want to take too much of your time. But what is the relation between these notions of bounded variation and the more general notion in higher dimensions that relates to the gradient? So like, if you had characteristic functions that would correspond to finite perimeter and so on.
Yeah, I do not know. I do not know. Yeah, I don't know. So that's my, so are there other questions? Okay. So, the theorem 4 that we will see in one dimension is this. So now I just want to say a little bit about what happens. What about the discretization itself? Okay, I'm going to just what do I mean by discretization? Okay, so suppose you have like a wavelet-like family, and you suppose that to every dyadic cube, you've got a family of disjoint subcubes whose union is all of Q, so it's a partition of Q. And so for any function on L1 of Q, you can this F condition on G of Q is F averaged on J, characteristic function of J, where the J are in here. The usual, just replacing F by its averages over a subcube. Okay. So now, because I don't want to pick this up too much, take too much time. If F is it turns out that if F is an NBV of Q, and this G of Q consists of identical subcubes. Okay, so you partition Q into identical subcubes. They don't need to be dyadic, just identical subcubes. Then this function here is also an NBV of Q, and that's actually pretty straightforward. Okay, and so therefore this family here would also be almost orthogonal. Okay. What's interesting is that, of course, if F, this says that if F is if these functions are held or continuous of order 1, like that they're wavelet-like, and you replace them by averages over subcubes, which don't need to be in any way nicely behaved, you still get an almost orthogonal family, which is kind of great, because you've just really, the discretization has totally destroyed the smoothness. Okay. Now, same kind of, if you look at the same kind of discretization, but now you ask that every J and Q be small. Its length is small relative to Q. Then if you have an NBV family up here, and you look at how far is this family from this family and the almost orthogonal norm, turns out it's no worse than like tau to the 1/4. Okay, so this is nearly the same as this family in terms of its almost orthogonal like properties. Okay. It turns out that if these guys, in these J's here, are all dyadic subcubes, and they're all uniformly small, you get a better estimate. That's because dyadic cubes are always nicer. Okay. So 3 more. If that original initial family is wavelet-like, and suppose you have these discretization where all the cubes here are dyadic, okay, then in fact the difference, the almost orthogonal difference here, is in fact nice. It says it goes down like tau to the alpha, okay, and then number 4 here is if you have started with a wavelet-like family for alpha equals 1, then and you do the thing with the dyadic cubes, then in fact this family is basically an NBV family times a factor. This is as a fairly straightforward proof. Okay, so the practical meaning of all this is that if you have start with a wavelet-like family with alpha equals 1, then if you believe theorem 4, then the discretizations I described there are stable with respect to these perturbations. Okay, so now I want to show some pictures. Okay, so to show you what I mean about discretization of wavelet-like families. So here's a very simple function. Can everybody see that graph? Everybody see that graph? Anybody not see the graph? It's just sine 2 pi x. Great. Sine 2 pi x, 0, 1, has integral 0. It's wavelet-like modulo a constant. Okay, and what happens? If we can a discretization of it would be something like this. You replace the function by its averages over every interval of length 1/5. And of course, if you look at if you take a function like this, scale it, translate it appropriately on all the dyadic intervals, you get an almost orthogonal family with a nice constant. It's not so obvious you're going to get it with this, okay? Because the discontinuities here, you see, because these are intervals based on 1/5, okay? And you're looking at the dyadic intervals, not so clear you're going to get an almost orthogonal family when you do that. And of course, you could also have mix them up. Some of them have 1/5, some of them might have 1/7, maybe some of them might have, where is it, right here? I had another one, 1/16. Or you could have some of them have totally random partitions like this, okay? But the theorems I've been talking about, they say that if you have families of functions appropriately scaled and translated of these weird things with crazy discontinuities, they'll still be almost orthogonal, and you have control over the almost orthogonality norm, okay? So those are all my pictures. All right. So so what I said I was going to prove back here, Theorem 3, okay? I'll prove this, and that'll basically have most of the ideas that go behind everything else, okay? Theorem 3, and then I'll sort of show Theorem 4, try to show Theorem 4, at least in one dimension, okay? So Theorem 3 was the one about the basic almost orthogonality result for NBV families. So if it is a very easy lemma. If I is an interval and you have a function defined on I, have a bounded variation on I, suppose that B is an L1, real valued, integral 0, then this inner product here, is less than or equal to 1/2 the total variation of f on I times B's L1 norm. And I'll leave it to you. It's not that hard to prove. It's really a very simple thing to prove. Okay. Now, the next lemma is something we use to do an induction argument. Okay. See, we're first going to prove Theorem 3 for D equals 1, and then induct on D. Okay, induct on the dimension. So Theorem 2, lemma 2 is basically what allows us to do this induction. Suppose that we have the dimensions at least 2. Q is the cube. F is an NBV of Q. We're going to factor Q as its x1 Cartesian factor with crossed everything else. And for y in Rd minus 1, I'm going to have phi of y is L of Q to the minus 1, integral over I1 of Q, ft y dt. Then this function here, phi, is an NBV of k of q, of this leftover thing here. Okay, because I see it's 1140, I will not go through the proof in detail. It is up there in the notes. It's basically a matter of bounding sums like this with certain points in Rd minus 1, and it basically comes from the fact that these sums are controlled for f, because f is an NBV, and then just integrating a bunch of sums that are all bounded by 1. Okay, so nothing to it. Okay, so we get that. We get that. Okay, so now we can prove Theorem 3. Like I said, we're first going to do D equals 1. All this is, we're using the good old Schur test for sequence operators defined in little L2 of the dyadic intervals. So we're going to bound the inner products of our functions we're trying to show almost orthogonality of with the Haar functions, okay? So now if I is not a subset of Q, so that means that, let's see, that means that either the right or left half of I totally contains Q, or they're disjoint, then of course this is 0. So otherwise, if I is a subset of Q, then we can actually bound this using lemma 1, okay? Using lemma 1. We know what the L1 norm of this is. What we're going to get is 1/2 total variation of f on I, and then I over Q raised to the power 1/2. So for every dyadic interval Q, we can sum over all the dyadic intervals I. Of course, you only get the i's that are contained in Q. So you're getting all these. Let's see, k equals 0 to infinity, I of Q, 2 to the negative k, blah, blah, blah. These inner products. 1/2 q, 2 to, let's see, so you're going to get this thing here. This is going to be for each k, this is going to be 2 to the negative k over 2. There you go. And you get the sum of the variations, but of course the sum of the variations of this is 1. And so you get this, and then you sum that up, and you get that. There you go. Meanwhile, back at the ranch, for every fixed dyadic interval I, you sum it the same way, sum over all the q's, and you're going to get 0 to infinity, q, blah, 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 and you get the same thing. And of course, now this thing here, this is the total variation of f over I. Remember, q is contained in I, and this, of course, is bounded. This is, of course, bounded by that. You get 1. And of course, you only get one term here because every interval I is contained in only, in at most, one such q. So you get the same sum, and you get that. And so therefore, if you consider this mapping, going from little L2 of D1 to little L2 of D1, defined this way, T of the sequence is what you get by taking this matrix and applying to this, applying it to this vector. By the Shor test, T's operator norm is less than or equal to the geometric mean of those two numbers we got here, which is, of course, just that number. So T extends to a bounded operator on little L2. Great. So cool. Let's see. So now let's suppose we have F. It's finite. F is a finite subset of little D1. Little f is this finite linear combination. And we're going to use the fact that the Haar functions form a complete orthonormal system in L2 of R. Go like that. So this is the sum of these inner products squared. But of course, f is that sum. So there we go. Yeah, it's just that. But of course, we have a bound. This is now just going to be the little L2 D1 norm squared of what T does to that sequence. And of course, we have a bound on that. So there you go. So for in one dimension, we prove theorem 3. Okay, we have that the L2 norm of this sum is bounded by this number times the sum of the squares of the square root lambda q's. So now we're going to do our induction argument. We assume that this result worked for d minus 1, which is at least 1. We're going to do it for d. Okay, so we assume we have some constant depending on d minus 1. So that this works for all. We have the result working for things in rd minus 1. So now look at a guy with the cubes are in good old dyadic cubes in rd here, and these are an NBV of q. We're going to take fq of x, whether it's fq of x prime y, where x prime is an r and y is an rd minus 1. We're going to write fq x prime y as f1 x prime y plus f2 x prime y, where f1 x prime y is going to be our original function minus what we get by taking our function fq and taking its average in the first variable. Okay, we're basically subtracting off its average in the x1 variable and then multiplying by this cutoff here. Okay, cutting it off to only live in the q, and then f2 is just the average with that. Of course, this is legitimate, of course, because fq is supported on q. Okay, so you look carefully here. You see these guys here. For every fixed y, these functions here, we almost orthogonal in L2 of R. Okay, you look carefully. I mean, if you fix y, what you have in x prime is a family of functions basically that are basically NBV functions supported on dyadic intervals. Okay, some of these that's for all of the cubes for which this thing is not identically 0. Okay, so this family here will be almost orthogonal in L2 of R with constant bounded by c of 1. Okay, to explain it in detail, this is because again this guy is either identically 0. It means q doesn't come anywhere near it. This set, or it's a suitably scaled, uniformly bounded variation function with interval equal to 0. That's because we subtracted off the average, okay? And I just want to note that subtracting off the average does affect the total variation of this function, but it doesn't affect the Schur norms. It doesn't affect total variation on I, as it does not affect the relevant Schur test estimates. So now if you fix y and look at this sum, lambda q q to the minus 1/2 fq x prime y d, and then integrate just dx prime, using our one-dimensional result, we get it's bounded by c of 1 squared. Now let's see, we have this thing minus 1/2. We're going to put a L of q to the minus 1/2 with that. That gets taken away. We're going to take the rest of this measure. That gets absorbed into the lambda q. We have this thing squared, and they also get the characteristic function of kq of y. Okay, notice we had this thing up here. Okay, so we're basically taking this and the rest of the measure of q, so to speak, and absorbing it into the almost into the sort of linear combination here. So for every fixed y, the interval of this dx prime is bounded by this. And now, of course, you integrate dy, and what happens is that this gets canceled off because the measure of kq of y is L of q to the d minus 1. And so you get that, okay? Cool. Now, by induction, I say, let's look up here. Remember this guy, as we showed, this guy is an NBV, will be an NBV of k of q. So now by induction, for every fixed x prime, this family here, the F2s, is almost orthogonal in L2 R d minus 1 with constant less than or equal to c of d minus 1. Again, it's the same business with just looking at what happens with the hyperplanes here. Okay, what's going on with the other dyadic cubes. So if you now fix x prime and integrate dy, one of this family, what you get, this is less than or equal to c of d minus 1 squared, lambda q squared. Now you get L of q to the minus 1. Okay, you basically peeled off most of the measure of q and put it with the lambda q. What's left over is here. Chi q, then you have chi I 1 of q x prime. Now you integrate x prime. Bingo, dy dx prime. You get c of d minus 1 squared. Put these together, you get that when you sum up with the total function, you get c of 1 plus c of d minus 1, lambda q squared to the 1/2. And of course, that's saying that then the constant d is going to be bounded by d times c of 1. It goes up by c of 1 each time, and you've controlled that. Okay, so well, I'm really running out of time badly here. Well, let me just say a word about what happens in Theorem 4. Okay, Theorem 4, that is the one with the perturbations. Basically, turns on this little lemma. Suppose you have a function of boundary variation on R, and you have a function psi of this very simple form. Where is it? Alpha x plus beta, and look at a function like this, f of x minus alpha times f of psi of x, okay? And integrate that against a function of this form, characteristic function of an interval minus characteristic function of an adjoining interval. Then you can, the inner product between these two functions is smaller than or equal to one of, well, it's a sort of complicated mess, but it's not too bad. You get total variation of f on a certain interval. This is a convex hull of some intervals that arise from this interval j, and also what happens to j under a function psi. And then you get these differences in characteristic functions of intervals. And it turns out that we can control these. We can actually control these things. Okay. And why is this true? Why do you get this strange thing? Because g times phi, that's f phi minus, well, we just do a change of variable, f phi psi inverse. This is f times this. Now, the f times this difference here. This function is a boundary variation. This function will have small L1 norm if alpha is close to 1 and beta is small, okay? Because you're just taking intervals and shifting them around and maybe dilating them a little bit. You're not doing much to them, okay? Okay, and so we can use this down here, this lemma 5, suppose you have a bounded interval with center xi, and you have real numbers, which are alpha is close to 1, tau is close to 0, and you have this function psi, alpha x minus xi plus tau length of I, x of I, and you have f as bounded variation. If you have a subinterval of I, which is not too small, if you take f minus alpha psi times something like this, then it's bounded by eta, length of I, and then the total variation of f over j, over the triple of j. And that comes from some simple geometric arguments, which basically said that you see when you're doing this, f minus alpha f psi against this is the same as f against a corresponding sort of shift against these functions like this. And you understand these things. You're shifting intervals by a little bit and maybe dilating a little bit. And you can understand that something like that has small L1 norm, okay? So I am running out of time here, and I'll just, here it is, yes. The meaning of lemma 5, which is sort of the key to the whole thing, is that for the sort of f we're looking at, the inner product of in parentheses, f minus the perturbation of f with a Haar function equals the inner product of f with, in parentheses, a Haar function minus a perturbation of a Haar function. And the thing is, that second thing will have small L1 norm, okay, because of the special form. So even this is, so what you're in a way exploiting here is a kind of smoothness in the Haar function, okay? Okay, so like I said, because the Haar function is special form, the second factor will have small L1 norm, and then you can use that first lemma to bound the inner product, okay? So maybe the last thing I'll say here is that lemma 6, suppose you have a whole family of functions like this. You have a whole family of functions indexed over the dyadic intervals. You have numbers alpha I and tau I, which are, okay, alpha i's are close to 1, tau i's are close to 0. Functions psi I, like this perturbing function, and a function fi that first of all has total variation less than or equal to 1. It's supported inside I, and also when you perturb it, when you have this little change of variable, that's also contained in I. G sup I is f minus the perturbation. Then it turns out that this family of functions will be almost orthogonal in L2 of R, and its constant will be no bigger than something times eta to the 1/2. Okay, it uses these results back here to do this, and again, it's just the Shor test plus being more careful. You have to split the sum at roughly interval having size eta. Okay, and then you just sum things up properly, and you get that the Shor test estimate you get is now going to be basically eta to the 1/2. Okay. I'll just say this is all just technically keeping careful track of what happens when you do the Shor test on this funny thing, okay, where you now have these good control on these inner products. Let me see. So just a word now about what about higher dimensions. In higher dimensions, you have to do this same sort of business, but now you have to do you have to control. You have to do the sort of slicing argument I talked about earlier, and you also have to do the fact that if you're moving a thing around with a matrix, you're going to need a stronger condition than just that bounded variation on coordinate parallel lines. You're going to need it on all lines. That's where the strong normalized bounded variation thing comes in. But even then, you need some way of somehow reducing these matrix transformations to things that look like these one-dimensional shifts and translates. And that's where I used this nice theorem, which is in the SciAm journal from a few years back, that lets you basically you could, if you take a matrix that's close to the identity, you can do the good old LU factorization, and L and U will both be very close to the identity. And so then you have to do this sort of slicing argument I described earlier, but you got to do it twice. You got to do it for every variable going down, every variable going back up, and show that these shifts are then not mucking up the almost orthogonality norm too much. And I guess that's all I'll say. And I didn't get to say anything about LP, but I think this is a good place to stop. The LP thing is some Littlewood-Paley theory, and a trick. And I guess I'll stop now if anyone has any questions, and I will go back and fix that typo. I apologize for that Haar function thing in the beginning. I will change those measure of I to the 1/2 to negative 1/2 to ones. But I guess I will stop now. And should I stop sharing the screen?
No, not necessarily.
Okay. So and if anybody is interested, I can send some preprints, and haven't given a talk in a while, and this is the first online talk that I've given. So I apologize for going over and having too much material.
Well, I interrupted you for a while, so I guess.
Could you say like 1 or 2 words about LP?
Sure. Well, LP. Okay, LP. So let's suppose the second result by the LP stability uses some basic Littlewood Paley theory and a trick. So here's the basic fact. Suppose you got a bunch of numbers in C, and you define this thing, okay, S lambda of X, chi I lambda I squared over measure of I, the good old square function, but it's now applied to these coefficients, okay? And then of course, this series here will converge in LP, 1 less b less than infinity, if and only if, of course, this thing here is in LP. That's a good old Littlewood Paley theory, okay? And of course, the function you get and this function here have basically the same LP norm or similar LP norm, okay? And of course, that's what the lambda i's are, we all know. And of course, if f is in LP, then of course also, and lambda is this thing, then you get this thing will be in LP. So now here's the trick. Suppose you got a family of L infinity functions such that they're supported on Q, and suppose that the almost orthogonality size of this family is bounded by 1. So now let's let lambda be this collection of numbers, inner product of f with these guys here, for f in LP, Q infinity. Then this thing will be no bigger in size than a constant depending on p times the LP norm of f. That is, you don't need Haar functions. All you use is the almost orthogonality size. Okay, and and of course this is just tested in L2, but you get this for LP, p less between 2 and infinity, and it depends on this this elementary result that take s of lambda, s lambda squared v dx, where v is a non-negative bounded function or L1 function. This is bounded by I should have had is bounded by f squared mv. Yeah, f squared mv. Okay, so if lambda is this, you get this, and it's really easy. It's the proof is outlined here. And of course, once you have this, well, then you have that the LP norm of this is bounded by a constant the LP norm of this of f by just doing a duality argument, v and mv, and of course the LP boundedness, or rather L p over 2 prime boundedness of the Hardy-Littlewood maximal function. Okay, is that clear? That's following more or less. Once you have this, then this, of course, immediately gives you that the LP norm of this, of s of lambda, is bounded by a constant times the LP norm of f for p in this range, p between 2 and infinity. Okay, once you have that, and the proof is quite simple. For k equals 0, plus or minus 1, etc., etc., ek is a set of cubes having this property, v, where the average of v is between 2 to the k and 2 to the k plus 1. And you're going to let u sub k be the union of all these cubes, q's and ek, and you notice that u sub k is a subset of the set where the Hardy-Littlewood maximal function of v is bigger than 2 to the k. We're going to call that m sub k. So just write this out. This thing squared v, you just write it out, inner product squared vq, sum it off over k, ek. These vq's are all controlled. We can take it our 2 to the k plus 1. We get this. And now the thing is that we can now notice that this is the same as this. As you see, f integrated against fq. Fq is 0 outside q. So this inner product is the same as this inner product. Okay? And so you can go, this is less than or equal to this, because these things are almost orthogonal with norm 1. almost orthogonality. So we get no bigger than that, which is, of course, no bigger than that. Now you just rearrange things. This is less than or equal to f squared, this sum, and there you have it. Okay. So now by homogeneity, if the almost orthogonal norm had been less than or equal to delta, you would have got a delta. So now suppose you got like Haar functions here, Haar functions here, or they're the perturbed guys, okay? And these are the plus or minus 1 ones, not the ones I screwed up on. So, and suppose that they are perturbed in the way I described earlier, then this difference, their almost orthogonal size, is bounded by eta to the 1/2, okay? So, well, here's f, which here's f basically, minus the perturbed f, hi. So that is that. But you see now, this family here has this small almost orthogonal size, and so I'll use my previous result. This will convert as unconditionally in LP to some function psi with an LP norm no bigger than constant eta to the 1/2 times FLP. Does that make sense? Does that kind of make sense? Okay, it's just Littlewood Paley theory and that trick with the maximal function. Okay, and unfortunately, I don't know how to. I would love to do this for p below 2, but to do that, I would have to have something, I think, like well, back here, like this for p less than 2. I don't know how to do that. I have control of this sort of almost orthogonal, NBV kind of square function for p bigger than 2, but not p less than 2. I don't know what to do with that. I've been batting my head about it for a while, a long while. And so this is just saying something about what happens when you try and do this in higher dimensions, where you have to have that funny factorization theorem. And the LP thing works also, because once you get this almost orthogonality bound for these Haar functions, you then get everything else. So are there other questions?
Can I ask? Hi, Mike. Hi. Oops. Let me.
Hi.
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 Hi, Galia. Hi. Happy to be in Canada today.
Yeah.
Greetings from New Mexico. So this may be completely but can you do some of these? So what happens if you have a two ways for the L2 theory? Can you
Yeah.
prove the same and then maybe extrapolate?
That's what yes, that's one thing I've tried. I've tried, like, say, yeah, let's do the L2 A2, that'll give you the universe. But yeah, it's the trouble is that these NBV functions can have discontinuities in all kinds of crazy places. You can't really do like a stopping time argument on them the way that you can with the Haar functions, because if you say stop, if you take a finite sum of Haar functions and you stop them at a certain point, then you know that everything that happens past that point will depend on other Haar functions that aren't in your stopping time. But these guys have discontinuities, possibly crazy place. So if you stop them on cube Q, well, on a scale smaller than Q, they're still going to have jumpy garbage there. And so if you do things like, say, you take, say you want to get, say you want to bound this NBV family sort of square function like this for p between 1 and 2. And so the natural thing is you take f and you break it into the good function and the bad function. You do the Cauldron-Zygmunt decomposition, good function and bad function, and the good function is still good. The good function is fine. That's in L2. You've got an L2 bound. You can do that. The bad function, you want to get some kind of weak L1 bound on that. But of course, the bad function is built of these functions, these functions B, which are just integrable. They have integral 0. They're on cubes, and they have all kinds of crazy stuff going on. And the trouble is that you're now going to be integrating. You're now going to be taking inner products of them with these NBV guys. They have crazy discontinuities that won't be, for example, constant across the supports of these guys. So I mean, for the Dyadic square function, trying to prove its LP boundedness for P between 1 and 2 is easy. You just split it function F into good and bad, and then you can see you can then get that you then say, so now we want to show that the measure of the set where S of F is bigger than lambda is small. So we look at the things that are say away from the bad cubes. The only square functions terms you're interested in are ones that are going to have, the Haar functions will be constant across the B's. Across the B's, that's fine because the integral is 0. But if you have these guys, you see, they will now be, these NBV guys are jumping up in crazy ways, and the inner products of them with the bad functions B sub q, BQ, not so good anymore. Am I making any sense? Is this making any sense at all? Maybe not.
Yeah, but maybe you can make the B's better. You can make.
There's one idea I had of like try to make the B's better. One was to
partition of unity kind of thing.
I tried making the B's better. I tried also breaking them into families where one of them would have cancellation on every for each one of the D directions, the D standard directions in RD. You can break them. You can break the B's. You can do you can break break them into like D families, where in each family these guys have cancellation along every line, in this direction. So, but I've tried a bunch of things, and each time you run up against the fact that these guys here can have discontinuities, everywhere, and somewhere or other you do have to face the fact that the bad functions B have to be bad somewhere. The bad things don't go away. You do have to deal with them somehow, and they do end up getting interproducted with things like this. And I guess I wish I had a blackboard. I guess I wish I could actually run on a blackboard here to show what happens. But if you try to show, for instance, that the dyadic square function is a weak type 1,1 using the Colburn-Zygmunt decomposition, you'll see what I mean. You break F into the good function or the bad function, and then the square function of the good function, the place where it's bigger than lambda is less than constant over lambda, no problem. The place where the bad function is, well, then you do it like, at a piece at a time for every one of each one of the sort of pieces of the bad function. And what you'll find is that, okay, well, the sum of the support cubes for the bad function, that's less than or equal to a constant divided by lambda over, measure of F. That's the size. So fine, that sets control. But look at the set where X is not in one of those cubes, where the square function is bigger than lambda. And so then you're only dealing with taking inner products of the bad functions here with Haar functions, which are sort of big, have big supports, and which are actually constant across where the bad functions live. And those integrals are all 0. So there's nothing to prove. But that doesn't happen here with these FQs. You've got you take F, you break it into the good function, the bad function, the square function, even in this sense here of the good function is fine. It's fine because it's bounded in L2, no problem. But then for the bad function, okay, again the sum of the measure of the supports of the bad function pieces, that's bounded by F's L1 norm divided by lambda times the constant. That's good, no problem. But and so you're going to look at X that's not on any of those cubes, and you're going to look at its square function right here applied to a bad function over here. So you're looking at these FQs that are big, and you're going to take an inner product of a big FQ against some B of Q. And the trouble is this big FQ is not constant across the support of that function BQ. It might have all kinds of wacky jumps, and you don't know what BQ is, and so I don't know what to do. So yeah, so I keep thinking about it. I keep trying this, I keep trying that, and I think I kind of get the idea that the original argument back here that proved Theorem 3 right here, that if you have an NBV family, then you get the almost orthogonality with this control. What's going? This is very much an L2 result. Okay, it works on L2, and what's happening here, I think, is that there's really some subtle cancellation going on, which the Shor test estimate somehow lets us, sweep it under the rug. And so we're able to somehow control or exploit some subtle cancellation going on in these things without really understanding it. And that's what I think I need to do, is to understand the cancellation that's going on, really understand it to handle it for LP, P less than 2. The thing for the result for LP, P larger than 2, that's this trick. I mean, you're really not understanding the cancellation going on any better. It's that maximal function trick. Okay, so it's not really no new ideas, but somehow there's some kind of subtle cancellation happening here. And I keep one approach I return to now and then is say, maybe what I need is kind of like a local Shor test. That's kind of very, very vague, but the Shor test is kind of this global object. It says it's bounded on all of L2, and it doesn't. I mean, the way it's phrased is just in terms of inner products of these functions, which could be living, somewhere. We don't care, and so you get this boundedness, on L2. But the LP stuff is somehow, I'm not saying this very well. Well, that you sort of want some kind of control on what's happening, like locally, and maybe you want some kind of local control on the square function. There's got to be some kind of like a localized form of the Shor test that maybe could help. You need better control of the square function, because basically for a function in L2, all you have to do is know the size of these coefficients, whereas for a function in LP, you need not to know where the size of the coefficients, but also where their support functions lie. Where the Haar functions lie. If you shift around, if you take a function in L2, say, and permute the Haar coefficients, so you assign them to different Haar functions. Of course, you haven't changed the L2 norm. You do that in LP, I don't think so. Okay, you take a function in LP, shift its Haar functions, permute them over all the Haar functions. I don't think you're going to stay in LP. I haven't tried it out, but I rather doubt you would stay in LP. And the Shor test, in a sense, doesn't see that. It just does this bound for all the coefficients. So I think what I need is some kind of a localized form of the Shor test, to make this work for small p. Hope I didn't confuse people too much, any more than I confused myself.
I have a couple more questions, but I don't know if maybe other people in the audience, because maybe this is getting too technical, so we can.
Yeah, I don't want to frighten people too much.
Yeah.